Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss quantization. So what is quantization and what is the purpose of quantization and what is the quantization noise is appearing when you convert an analog signal into digital one. So these topics are going to discuss in this session. So let us going to start quantization. So first, quantization. The sample version of the message signal is then quantized, thereby providing a new representation of a signal that is discrete in both time and amplitude. So before going to quantization, once again we are going to remember PCM. In PCM, we're having three important blocks. One is a transmitter block, and another one is a regional repeater, and third one is the receiver. So in the transmitter, we are going to convert an analog signal into digital one by performing three operations. One is sampling, quantizing, and the third one is encoding. So these are the three operations which are done in transmitter of a PCM. So let us see the blocks. So this is sampler, and this one is quantizer, and this one is encoder. So here, what is the input of a sampler? It is an analog signal. So here my source which producing analog information. So we can know the analog signal is nothing but a continuously varying signal, simply essentially signal. Okay. So by applying this analog signal to the sampler which is going to sample that analog signal. So here the sampling process is done according to the sampling theorem. So here I am going to discrete the time domain. I am going to discrete the time domain. Why? Because an analog signal having both time and amplitude. So amplitude is taken on y-axis and x-axis is taken as the time scale. So my sampler which is going to convert the continuous time sample into the discrete sample. So continues to discrete sample. So here the output of the sampler is discrete like this. So this is the instance, discrete instance. So that's why here I am saying the sample version of the message signal. Here my input to the quantizer is the sampled version. So here my time is only discrete, but my amplitude is in continuous form. So here when you going to encode any signal, before it must be in discrete form in both time and amplitude. So after sampling, only time will be discrete, but amplitude as continuous. So here we are going to convert that continuous amplitude into discrete amplitude. So this is the main purpose and main importance of this quantizer in analog to digital conversion. So this quantizer must be used in digital signal processing, any conversion of analog to digital. Okay. So here the definition we are taking: amplitude quantization is defined as the process of transforming the sample amplitude m of nts of a baseband signal m of t. So here m of t is nothing but our message signal. By applying this message signal m of t to the sampler, it is converted as m of nts. So here, students, you can recognize this m of t is a continuous. M of t is the continuous. So by applying this continuous signal to the sampler, it will be as this. M of nts sampled version is coming. At a time t equal to nts, the n is the number at what samples are taking, how many samples. It may be 5, it may be 10, it may be 100, it may be 1000. So how many samples are taking? It is n number into a discrete amplitude. So here I am going to convert this m of nts into v of nts. This is taken from a finite set of possible levels. So here we have a doubt how this quantizer is converting continuous amplitude into discrete. Here they uses this discrete amplitude levels called quantization levels or representation levels. These levels are predetermined. These levels are predetermined. So how this is done? This is done by approximating the amplitude of each sample value to the nearest value from a set of predetermined discrete amplitude levels called quantization levels or representation levels. So here I am converting continuous sample into discrete sample. So why I am using sample? Before quantizer having a sampler. So I am using as a sample, continuous sample. Why continuous? The amplitude is continuous. So my aim is convert this continuous amplitude into discrete amplitude. Okay. So here L. What is L? L is the total number of amplitude levels used in the quantizer, or we may be called as representation levels or quantization levels. What it may be. Here L is the total number of amplitude levels. Why? Because in quantizer this discrete is converting. That means amplitude conversion to discrete by approximating to the nearest value. Why? Because this amplitude levels having some amplitude, but my continuous amplitude is a round off to the discrete amplitude. That is quantization. So here you can see, this is the picture you can identify. This is analog signal we're taking, and here I'm taking L levels. Here this is L. This L is called as representation levels or quantization levels. And here it mentioned delta. Delta is the step size. Step size means the spacing between two representation levels or quantization levels or amplitude levels can be called as step size. So here you can see. Here we can say this one as in between these two levels. Here I am using 10 levels. You can see 1, 2, 3, 4, 5. Again in other side I am using same 5 levels. So how many levels I am having? Totally my L is 10. My L is 10 levels I am using. By using 10 reference levels, I am going to convert the continuous amplitude into discrete amplitude. Here what I am going to do? Here I am going to round off to the nearest amplitude. Here I can round off 2 or round off 3. Why? Because it is in between. So exactly 2.5 amplitude having. So I can round off layer 2 or 3. Or in some cases, it is just as a 2.6, or here you can see this one. So this one is nearer to 4. It may be as a 4.3 amplitude. So here I'm going to round off to this level. I'm going to round off this level. So I am converting continuous amplitude into discrete amplitude at this level. So totally I required 10 levels. So how did you know how many levels are going to use? So this is justified by we can take in how many bits are going to encode. Why? Because after quantizer we are having encoder. So this encoder which is going to encode these discrete samples into a bit form. So it may be encoded like this 101 like this. So here I used 5-bit code. My n size is 5. So how many levels are required? It may be 2 power n. In some we may use the parameter or rn, what it may be, to represent this number of bits in a code. So here I take in n. So what is this one? 2 power n. 2 power n means 2 power 5. So 2 power 5. That means 2 into 2 into 2 again into 2. So 2 2s are 4, 4 2s are 8, 16, 32 levels I required. I required 32 levels for a 5-bit code. Or my encode is 4-bit. So L is 2 power 4. So nothing but 16 levels required. 16 levels I required to convert this continuous amplitude into discrete. Okay. So this is the way how the quantization is done in quantizer. So here the characteristic, the quantizer characteristic is described by staircase function. Here V is the output, M is the input, and G of M which defines the staircase function. Staircase. So once again you can sit back. Here this is just like staircases. Like the staircases. So how this one get? This one get by this V is equal to Z of M. So this quantizer characteristic is nothing but a staircase function. So this staircase function which can be applied to the analog signal, it is going to round off to the nearest value. Is nothing but quantizing is done. So now quantizers types. So how many types of quantizers are available? Here we're having 2 types. One is uniform or non-uniform. In uniform quantizer, the reference levels are uniformly spaced. Otherwise, it can be called as non-uniform. Why? Here we can see delta. This delta is nothing but step size or the spacing between 2 reference levels. So what is this one? Delta is equal to 2m max by L. Here what is L? L is nothing but my reference levels. So again L is related with 2 power n or 2 power r. So here n is number of bits is going to use to encode. Okay. So this is the relation between step size to L and L to n. So when you know these 2 formulas, you can solve a number of problems. Okay. So here my delta is uniformly spaced. My delta is uniform. That means the ripple levels are uniformly spaced, means the delta value is uniform. Then you can call it as uniform quantizer. Otherwise, you can call it as non-uniform. So again, here we're having 2 varieties of uniform quantizers. One is mid-treat and another is mid-rise. So Here this is input output characteristic of this quantizer. So here you can see the staircase approximation. Why initially we said V is equal to G of M. Here V is output. What is output? When you're giving the input, sampled input to the quantizer, it produces that output V. So V is the output. So here you're having two varieties of quantizers, uniform quantizers. One is mid-trade. Here you can see the origin is in trade, whereas this is rising portion at the origin. So this is called as mid-rise type, and this is called as mid-tree type. Mid-tree type. So both are symmetric, you can say. Both uniform quantizers are symmetric. Mid-trade or mid-rise type. Okay. So now the first one is mid-trade. So figure A, actually the first one shows us the input output characteristic of a uniform quantizer of the mid-tree type, which is so called because the origin lies in the middle of the tree of a staircase-like graph. Okay, staircase-like graph. So the origin is at tree type. And second one is a mid-rise. So here in the mid-rise, the origin lies in the middle of the rising part of the staircase-like graph. Already we've seen in that the second figure, the rising portion is at the origin. At the origin. So this is the mid-rise. So both quantizers are symmetric about the origin. Okay. And uniform quantizer having drawback, that is it cannot be used for speech signals. Why? In speech signal, some having loud passages and some having low passages, means weak passages. The weak passage having low amplitude levels, whereas loud passages having high voltages. So the uniform quantizer is failed to catch some weak or some high portions. Why? Their quantizer levels or quantization levels or reference levels are uniformly spaced. So when the drastic changes is coming in the signal, it failed to catch. So that's why we are going for non-uniform quantizers. Non-uniform quantizers. So here the sample version of message signal is then quantized, thereby providing a new representation signal is discrete in both time and amplitude. So sampler done this time as discrete and quantizer done discrete amplitude. So now the output of the quantizer is a pure version of discrete. So this pure discrete signal is going to encode. We are getting code. So that means analog to digital conversion is done. Okay. So this is the application where this uniform quantizer cannot be used. Why? Here the range of voltages covered by voice signals from the peaks of loud talk to the weak passages of weak talk is on the order of 1000 to 1. So there is a lost variation, very large variation. So my uniform quantizer levels are fixed, predetermined levels. So that's why in some cases it fails to catch that information which is going to convert in digitization. Here why I'm using all this, my aim is to convert analog into digital one. So each and every information is going to digitize. Okay. So that's why Here I am going to catch every information, but uniform quantizers or fail in some cases. So here I am going for the non-uniform quantization. So by using a non-uniform quantizer with the feature that the step size increases at the separation from the origin of the input to output amplitude characteristic is increased. The large end step of the quantizer can take care of possible excursions of the Y signal into large amplitude ranges that occur relatively infrequently. So, already discussed that weak passages need more protection or favor at the expense of the loud passages. So, in this way, a nearly uniform percentage precision is achieved throughout the greater part of the amplitude range of the input signal, with the result that fewer steps are needed than would be if the uniform quantizer were used. So that's why here I use a non-uniform quantizer. So the non-uniform quantizer does not exist in reality, but we are going to design that equivalent to the non-uniform quantizer just by passing the message signal through a compressor and then applying the compressor signal to a uniform quantizer. So that means here I am using a compressor. So this is my compressor and this is my uniform quantizer. So this both can be called as non-uniform quantizer. So this is my non-uniform quantizer. Here, before applying to the uniform quantizer, I am going to compress. So how this compression is done? Here we are following two laws. One is mu law and another one is Ye law. So here the expression which shows here three variables is there. One is V is the output, where M is the input and this mu is the compression parameter. This is the compression parameter. Depends on this parameter, my compression is done. For example, if mu value is 0, so what happens? Mu is 0. So here getting log 1 by log 1. So it is there is no compression. No compression is done. No compression is done means it is similar to the uniform quantizer. Okay. So here my aim is to show the steps. Why? Because generally V is equal to G of M. What is this one? This is the staircase like graph which is produced with this quantizer. Already we discussed earlierly. V is equal to G of M. So the step I will show. So how? Just here I am going to derivative. I am going to derivate this V. I am going to derivate this M. So what I get? I get here the slope, the reciprocal slope of this compression curve which defines the quantum steps. So here I am going to show the quantum step. You can see. After we can discuss this one and first this one. Okay. So the case of uniform quantization, mu corresponds to 0. So for a given value of mu, the reciprocal slope of the compression curve which defines the quantum steps is given by the derivative of mod m with respect to mod v. So that is dv. That means derivative of v. Derivative of mod v which is equal to 1 by log of 1 plus mu into 1 by 1 plus mu mod m into mu derivative of mod m. So finally, this derivative of mod m by derivative of mod v, which gives the reciprocal slope of the compression curve. So this is my quantum step. So where this mula is used? This mula is used in Northern America and Japan. In these two countries, this mula compression is used. Okay. So before slide again, once you could see, this one. So this is my Mueller compression curve. When mu is 0, the first one, the blue line, mu is 0. So what happens? Here mu is 0, there is no compression. So how can you say? When you consider the input level to the output both getting linear, you can see at low levels this is almost equal. Almost equal. That means here there is no compression system. Okay, the input is equal to output, there is no compression. But whenever the input value is more, the output is also increased. So when you take this one 0.5, here my value is almost 0.8. Okay, so that means here the input is increased. Input value is increased. The compression value also goes to increase. The output value is increased to 0.8. Okay, so when mu increases, the compression goes to increase. Here you can see mu value is given number of values. Mu is 0, 10, 50, 100, 255, 500, 700. What happens? The compression is going to increases. Okay. And another law is IARE law. So the mu law is neither strictly linear nor strictly logarithmic, but it is approximately linear at low input levels and approximately logarithmic at high input levels. So here we use another compression is called as IARE law. So this IARE law is used at Europe and the rest of the world. In Europe and rest of the world, you can use this IARE law compression. So the IARE law is defined here in two regions. Here it is taken as 0 to 1 by a. In one region, the input value is, and the input value is 1 by a to 1. So here also V is the output, M is the input, A is the compression parameter. One is the output and this one is input and this is compression parameter. This is the compression parameter. So here both laws, either mu law or IARE law, here we use 0 to 1. It is normalized. It is normalized. So unit value we are taking from 0 to 1 by a is one region and 1 by a to another to 1. So here M is the input. My input lies in this region. We can take this first formula, that is A mod M divided by 1 plus log A. But if my value changes in between 1 by A to 1, here we can take 1 plus log of A mod M divided by 1 plus log A. So this is IARE law. And here also I required that quantum step. So the reciprocal slope of the second compression curve is given by the derivative of mod M with respect to mod V. So this is my quantum step, and which is equal to 1 plus log A by A in the region of 0 to 1 by A, and again 1 plus log A into mod M, and in the region of 1 by A to 1. So finally, here the compression is done. And here also one graph is there, that is Euler graph. Here you can see the A value is 1, no compression is done, which is similar to mu value is 0. In the mu compression curve, that mu value is 0, there is no compression. It's just like a uniform quantizer. Here also when A value is increased, the compression takes place. Okay. So here also you can see from 0.3 to this, we can take some 0.8 value. Okay, more compression is done. More compression. The value is increases, the mu compression is going to increase. So this is Euler compression. So my dear friends, here you can take the quantization error. Earlier we are discussing quantization. So quantization, which is going to convert continuous amplitude into discrete one. So here some differences we can see. What that one? We are converting, or we are going to round off. We are going to round off to the nearer predetermined predetermined representation levels. So there is some difference between the input signal to the output signal. When you are going to round off the input signal to the nearer predetermined reference levels, we got some error. That error is called as quantization noise. So it is nothing but Q. You can define Q is equal to M minus V. So the difference between an input value and its quantized value, such as round off error, is referred to as quantization error. Okay, here earlier we taken this one. Here I am going to round off to the nearest value, but actually here it is in between these two reference levels. So it may be 2.5. The amplitude of this exact value is 2.5 volts. But what I am doing, I am going to convert or transform into the digital one by approximating to the nearest value or round off to the nearest predetermined reference levels. So here I am going to round off to this 2 voltage level or 3 voltage level. So but actually what I am having 2.5. So here there is a difference. So that difference is called as quantization error. So that is we are going to discuss. So that error, the difference between an input value and its quantized value or round off error is referred to as quantization error. So here again you can see the input value. So input value is a sinusoidal and quantized output here you can see. So that is the difference. So this is the error. So this error is called as quantization error. So this quantization error, it shows in the signal to noise ratio of the system. It impacts shows in the signal to noise ratio, SNR. So we are going to calculate this signal to noise ratio. So here we know that L is the number of reference levels and delta is the step size. So by knowing these two, why here my aim is to convert the continuous amplitude into discrete amplitude. So that's why I'm going to require the predetermined reference levels or quantization levels is called as L. So this L which is related with N, and the step size is the spacing between the reference levels, that is equal to 2m max by L. So by knowing these two parameters, I am going to design my quantizer. So when you are using the quantizer, the quantization noise must reduces. So that quantization noise will going to affect on signal to noise ratio. So SNR is signal to noise ratio is gives the performance of the receiver. So it is the performance. It shows the performance of the receiver and the quality of the signal. So SNR is which shows the quality of the signal. So is nothing but SNR is nothing but signal to noise ratio. Signal to noise ratio. Here this is the signal. What I am using, the signal. It may be M of t or M of NTS, okay, or V of NTS. But here N is a quantization noise. Here we are taking. Here it is taken as quantization noise. It shows as sigma square. So here we are going to find the sigma square and going to substitute in SNR. Then we are going to find what is the SNR of PCM. Okay. So in the next session, we are going to calculate this quantization error and what is the SNR value. So these two parameters we are going to discuss in the next session. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.